Zhang Jun to give us distinction lectures at DKU. And Zhang Jun have really have a distinct career. He working on the many things along the fluids, and including geophysics flow and bioflow, the thermal and everything. And he is always giving like the fabulous lectures in the public lectures. Sort of, I heard a number of times. He's extremely. So maybe if we should by his graduate from Wuhan University, our partner DKU, then he got the Ph.D. in Denmark, University of Copenhagen, and the professor. I know him, but he's an assistant professor at NYU, and built up the polymer lab, the fluid mechanics lab at NYU. It's really. Then he has now currently he also involved NYU Shanghai, developed some of his lab and sort of a lot of things in over there. Okay, I will be extremely happy to have him to give us distinct lectures on the group of locations in fluids. Zhang.
Great, thanks, Professor Liu. It's a great honor to give this lecture. Actually, this is my first time give a Zoom lecture, even though I've been teaching online for the past spring semester. Anyway, I'm still learning how to use Zoom because on different device like iPad or computer, they somehow behave differently. Okay, but let's work together. Let's have a good chat today. So it's a truly an honor to give this Zhu Chongzhi Distinguished Lecture for the Math Center at Courant University. We consider this is our sister university in the greater Shanghai area because I'm involved with NYU, New York University, Shanghai campus over the past few years, okay? And meanwhile, I'm also sharing my time with the Courant Institute in New York, also the physics department of NYU, okay? Maybe I should switch to my PowerPoint right now. Let me know how to do this, okay? Let me see how to move this one. Maybe you can cut me to the, okay. You see my screen?
Yeah. Yes.
Yes.
Oh, great, okay. Excellent. It's far more interesting looking at my screen than my face, okay? So good evening, good morning, or good afternoon, depending on where you are on the globe during this strange time. So here's the title goes like group locomotion in fluids. Group locomotion of what? I didn't make it clear, I apologize. So tonight, we're going to talk about animal locomotion, like birds and fish, and how they swim in groups, okay? And again, I'm honored to speak in this Zhu Chongzhi lecture series, okay? I felt this afternoon, while I was preparing the lecture, I thought I should prepare a slide, okay? A slide showing at least a picture of Zhu Chongzhi, okay? Here you see my little arrow here. That's a name spelled in Pinyin, so you can pronounce. Who lived? This guy lived 1,500 years ago, a little more than that. And I just learned from UA that he once was a county governor of Kunshan. And naturally, Duke Kunshan University creates the mathematical center in his honor, okay? I'm sure he didn't expect that when he was alive. And he was an astronomer and a mathematician, politician, inventor, okay, and a writer. Okay? as an astronomer, he measured the length of the year and the period of the lunar months precise within seconds, okay, during his time, which was amazing. He could start to predict solar and lunar eclipse during his time, which is also almost a miracle because as we know, in the good old days, people put a lot of myths into this eclipse, this heavenly phenomena across the sky. For example, 3 weeks ago, I went to Sichuan, trying to observe this annular solar eclipse, but the weather was so bad, I couldn't see anything. Still, I could record the brightness of the sky during this whole course. So I got some data because I'm also looking into these issues, try to understand if solar eclipse creates reduced solar radiation on the surface of Earth locally. We were wondering if that effect will create local wind. Okay? So that was the idea. That's why I've been following quite a few eclipse events. So far, I've been observing 4 of them. Okay. So come back to Zhu Chongzhi. Here I have a picture of him. Apparently that's a modern depiction of how he looked. I guess people just made up his look because for 1,500 years, there's not much left. It's like his many books in mathematics. He wrote probably like 6 to 7 professional books on mathematics methods, and they were all lost, which is truly a pity, okay? So his most distinguished contribution was to define to the correct digits for 7 digits for pi, the ratio of pi, okay? So here, if you see my arrow, he defines the number between this guy, okay, 3.1415926, and between this guy. So you can see it was correct, and it was very precise. And he held a record for 800 years until someone, I forgot the name, and had a better precision for the pi ratio from Europe. Okay? And his method, of course, is a classical method by constructing many polygons inside and outside to build in equality and to find out the arc length of a circle. Okay, so that's something I believe for people or for computers to figure out many digits of pi. We are still using these methods. Okay. And also, the owner not only went to him by naming a mathematical center at Kunshan University. There was also a lunar crater named after his name. Okay, so here, so the second last line, you see the Zhu Chongzhi was spelled differently. That's before pinyin was implemented in the People's Republic of China. So this is the old spelling in the good old days during the National Republic regime, okay, 70 years ago. So the spelling is different. And also there was a little asteroid in 1964. That was also named after him. Okay? So you can imagine that he has been internationally recognized. There's a statue of him in Kunshan. So next time if I go there, I will certainly ask the local friends to show me around. Okay, so that's the story of Zhu Chongzhi for this series of lectures. So I'm quite honored to show his picture again. Okay, so let's come back to what we're here for. That is group locomotion of animals. So here we have hundreds or maybe up to a few thousands of fish, making a large circle. They swim together. So we call them a fish school, okay? So the behavior called shoaling or schooling. So it depends, which, from where you studied your fluid dynamics or animal behaviors, you use different words. So we use schooling. That's much easier, the word to follow. Okay, and here's the fluid. Certainly that's ocean water. And also there's another fluid we call air. And birds, they fly in the air. They interact with each other, but first they become airborne by means of interacting with the air. So here you see bird flocks moving together. Sometimes the number can go up to hundreds of thousands. If people have heard of the story about the starlings, these little birds, over the Roman railway station, there was a lot of papers published from this group of animals, okay? And here you can see the pattern they make is very deformable. They change over time, okay? To our eyes, these collections of birds, they don't look very regular. They look very messy, okay? However, you don't see any collisions, at least I don't see it. No birds get injured by colliding into another bird, okay? So perhaps there's some orderly formation in the group, in the flock, okay? So here, again, those are the photos I randomly selected from the internet. I don't know, maybe I didn't do a very good homework. I don't know who took the photos. I will dig out in the future, right? Okay, so schooling flocking of birds or fish, I believe we all agree that's partly a social behavior. They want to stay together, okay? And partly is a physical interaction because they do need to interact with the fluid around. The fluid in turn will affect other individuals, okay? The social behavior, they want to stay together. Like us tonight, we stay together. We try to discuss an issue about swimming, about flying, okay? But very often we want to separate social behavior from physical interactions. So today, I hope in 45 minutes or so, you will be convinced that I'm talking about a physical interaction, okay? So of a school, of a flock, okay? So speaking of which, so how do I move this guy? Okay, I can move this one to the bottom, okay? And speaking of the models of flocks or schools, there has been a very famous model, has been well cited. It's called Weihs model. This is a Hungarian physicist, okay? And he invented a model, a very simple model, published 25 years ago in PRL. And this page showing 3 different variations of his model by Zumaya 2 years ago in Scientific Report. Okay, I just want to tell you briefly what the Weihs model is. For example, this blue arrow, that's me, okay? That's the one to be determined which direction I should fly into. And then what I do is I need to take a radius, say 2 meters around myself and count how many neighbors I have. And once I know all the neighbors' vectors, the direction of flight, I make an average, okay? And then I add a little noise because I don't have to behave exactly like what they do, okay? So that's kind of a mean field approach to treat this problem. So the variation can be, for example, in B, you don't have to take a radius of 2 meters, but you can count your nearest, like 7 neighbors. And then you do an average of these vectors, and then you fly your speed. And if you want to add a noise to your amplitude and to your direction, okay? And then furthermore, you can also implement, for example, you can add not only your neighbors, here you have 6 neighbors, and you can add 4 other important guys. Why don't we call them small leaders? So you take not only your immediate neighbors, you also take care of your, you take reference from your leaders, not too far away, because you really have to see them, and you do a vector average. So you can imagine this Weihs model can be modified and then can be simulated in 3D, in 2D, and you can also imagine the dynamics, the emerging dynamics can be very rich. They can move together, they can also split, they can also merge, and so on and so forth. But if we look into fluid dynamics, okay, here we have none, okay? So for physicists working in fluid, okay, air or water, this model is more like a social model, not a physical model, okay? You basically, you look how other individuals do, and then you make a decision, okay? Okay. So it's a little over the social part, not the physical part, okay? And then let's do a little physics here, okay? Because today we have a math physics lecture, and I happen to be a physicist by training. And worse than that, I'm an experimental physicist, okay? So whenever I talk about a problem, the first thing in fluid, the first thing I ask myself is this high Reynolds number, a low Reynolds number behavior, that's RE. The Reynolds number is actually the ratio between 2 forces. One force is the so-called inertial force. The other force is called the viscous force, okay? So give you an example, if I have a sphere, if I have a spherical structure, I put in the fluid is moving at the speed of u, okay? And then the fluid will come and hit this sphere, and then you have a force. This is called the inertial force because the fluid has to stop, okay? There's another force called viscous force. The viscous force is the fluid pass by this sphere and give a skin friction. And you can imagine this force and the inertial force, they have different expression. The ratio between the two gives rise to this expression, UL. L is the size of the object. Mu here looks like a V. Mu here is the viscosity, kinematic viscosity. So that gives a pure number. Typically, Reynolds number is for a bird or fish, for any sizable bird or fish, we're talking about 100 to maybe almost 1 million, okay? If we talk about a big whale or fast swimming dolphin, a shark. So we're talking about 10 to the 6, okay? So in that high Reynolds number, so we have all the forces will scale with velocity to the square, okay? The viscous force, by the way, scales with velocity linearly, okay? So we don't care about that because our Reynolds number is so high, the skin friction is negligible, okay? All right. So here I show a picture of this bird flying over water, okay? From the right to the left. Certainly, this guy needs a certain thrust. And then once you have a thrust, you have a speed. If you have a speed, you experience a resistance. So and then you have a terminal velocity. That means your speed doesn't change anymore. You have steady state speed. Once you have a steady speed, your thrust equals to your resistance exactly. Otherwise, you accelerate or decelerate, right? Because you have a speed and you have a wing, the wing has a certain shape, you generate aerodynamic lift, okay? And then that force balances with your body weight. That's why a bird can stay airborne, can stay in the air, okay? But for fish, you don't need this aerodynamic lift because the density of a fish is almost that of water, okay? So you don't need to generate extra lift unless you really want to move up for some other reason, okay? And on the right, I have a typical wind airfoil. Airfoil used for airplanes, okay? That's very typical, but up and down symmetric, called the NACA 17 airfoil, okay? But this wing has a direction, okay? It points to the left, okay? This is a very popular wing shape, okay? So what next is, okay. So we can actually, I didn't do the details. We can think about a dimensional analysis that gives the swimming speed or flying speed that is linearly proportional to the vertical flapping speed. So imagine my wing is reduced to an even simpler shape. That is a rectangular shape on the left, okay? The thickness is delta, the length is L, and here C is called the chord, C-H-O-R-D, chord length, okay? That's the span of the length, the wing. And then the vertical speed is amplitude multiplied by frequency. So this guy has a dimension of speed, okay? You go like that, up and down, okay? So imagine that here is a wing for a bird or part of the fin of a fish. It flaps up and down, okay? But overall, this bird is flying along this horizontal line, okay? Okay, let's pick up a typical moment. A typical moment that is the wing is flapping down, for example, that's a V, but you are also flying forward with U, okay? So your combined speed is this way. Combined velocity is along this tilt straight line, okay? So if you tilt your head with theta from horizontal, so what you see is this wing flying this direction with the angle theta, you will experience a lift force, Lx. This lift force in the horizontal direction, you have a component, this bluish arrow, okay? That's a thrust. So for people wonder, how does a bird get a thrust, get a force moving forward? It's actually from the lift force, okay? Yeah. So you can imagine if I change myself to 1.5 of the cycle, the wing will be moving this way, okay? Again, you will get, okay, I should move up, okay. Again, you have a similar lift force, okay? And then this lift force will balance with your drag. Then at that point, you have a terminal speed. So by working out these details, we get a flying speed of the wing that has a form like AF, that's a V here. So how fast you flap yourself, how fast you will go. And then with the geometric factor, that's a chord over delta here. So that's both lengths gives a pure number, okay? So that's a speed. So length L, this guy, because you are flying this way, okay, this direction. So L doesn't come into this expression. All right. All right. Okay. Another question, which, as I stated in the abstract, there are some surprises in this business, okay? So let me ask a question like this. If I have a totally rigid wing, okay? This is a rigid wing. You see this is rectangular. It's up, down, and the left, right, and in and out, symmetric. Okay, it has threefold symmetry. So I want to ask you a question. If I flap this guy up and down in the air, what will happen to it? Okay. So why do I ask this question? Because I want to trace what is the physical origin of flapping flight. So naively, let's do this. If I flap this guy, maybe this guy will move forward or the other way around. You might say that your wing is totally symmetric. How can you move in one direction? Okay, so you break the symmetry. Well, in many physical systems, we do have symmetry breaking bifurcations. Okay, but before showing that, let me show you how we did the experiment in the applied math laboratory many years ago. Okay, yeah. So here we do is we have a tank of water, and then we have a rectangular bar like that. It's connected to an axis, okay, like that. That's an axis. I will flap the whole thing up and down with a known amplitude and a frequency f here. I flap it, okay? But here, you see here, the arrow, and here, I have two ball bearings, allowing this whole thing, this gray part to rotate if you want, okay? So I flap this guy, that's a prescribed motion, but any possible horizontal motion of this guy would be the solution from the interaction, okay, between the water and the wing, okay? Okay, so let's imagine, if you still remember the animation I had in the previous page, I flap this guy up and down. If this guy wants to go this way, and if this guy wants to go this way, you would have a spontaneous rotation, okay? Or the other way around, okay? And indeed, to our surprise, yes, this system, once you flap it up and down, will spontaneously move in one direction with 50 and 50 chance, either clockwise or counterclockwise, however you define the direction, okay? Yeah. Okay, come back to symmetry breaking. So imagine here, I have a sphere sitting right on the top of this symmetric potential, okay? You see here, I have a nice symmetric situation, but this situation is not stable at all. Once I give a tiny perturbation to the sphere, this ball will either fall off, this time is from to the right, or it could fall off to the left, either way, okay? So our fluid system behaving almost like that, okay? So here, let me put in words, we have a spontaneous symmetry breaking, bifurcation taking place, okay? Which also means if God had designed a symmetric bird, we shouldn't worry about the birds. It could still fly in one direction, okay? Or the other, okay? Because it's symmetric, okay? Any questions so far? Or I'm talking to myself?
Now you are doing good.
Oh, okay, great.
I'm good too. It seems
Okay.
not be the solution because then half of the birds would fly backwards, but still I think there's something to come, right?
Yeah, well, very good point. You know, the evolution of animals, they follow very specific route, okay? They don't choose a mathematical form at the start. They do try and error. So you see birds, they do have a head, they have a tail, the wings, they have a leading edge, they have a trailing edge, okay? That follows evolutionary results. For that, they already broke the symmetry, so we don't have to worry about them, okay? Yeah. All right. I'm not so sure I answered the question, but let me move forward, okay? Yeah.
I'm okay.
Okay. So here, let me show you a flow visualization from this experiment we did 16 years ago, okay? So here, you don't see too well, that's a wing. It has passed the fluid following this trajectory, like the dashed line here in the lower panel, okay? And then you see all the fluid. If you put a little particles, you can visualize what's the motion of the fluid. You have this alternating eddies formed behind this wing, okay? Like this guy, like the bottom, okay? This structure has a technical term called inverted Van Karman vertex strait, okay? We all know Van Karman, okay? If you have like a stationary body in a fluid, you form a Van Karman strait. All the Van Karman strait, they have opposite spinning of each eddies, okay? That's why for this guy, it is termed inverted Van Karman, okay? So what is the nice thing about the inverted Van Karman? If you look at this guy, okay? It's rotating clockwise. The neighboring one is rotating like that. In between you have a jet, like that. Here in between you have a jet pushing water like that, pushing water like that. That means each time you flap your wing, you push water almost 45 degrees this way and 45 degrees this way. And then again, that's how you generate a momentum forward, okay? Of course, once you pick up speed, you experience a higher resistance, and then you will find out your terminal speed. You will settle there, okay? All right, and if you worry that our experiment has been in a rotational geometry, okay? And you might worry our experiment has been done in a 3D structure, 3D setting. So after our experimental funding, Salas Albon and Max Shelley, they also simulated our system using 2D numerics, okay? So here from the left, you can see it started vertical flapping, and then it lost its stability. It falls into flight, okay? Let me call it fall, okay? Because you really come down from potential on the very tip, and you fly forward like that. At the same time, you generate this inverted Van Karman strait, okay? Yeah. Okay, so that's for birds, okay, so far. For fish, it's very similar. Let me take a reference from Mueller's group, okay? She is a biophysicist, and in 1997, 23 years ago, they published a paper in Journal for Experimental Biology. She visualized the wake, what left by a fish. So here the blue part is the tail of a fish. The fish is moving outside of the screen, okay? And then leaving the fluid spinning in the tank. So she visualized, her group visualized the structure, showing that the flow structure in the fish's wake is also an inverted Van Karman strait. Okay, so if you want to go home to have a rest, stop listening. So the take-home message here is that for fish swimming or for bird flight, they have very similar mechanism to generate the force they needed to move forward. That is to generate an inverted Van Karman strait to push them forward, okay? Yeah. So fish and birds, they're the same, okay? And of course, once again, we come back to our title. So if we have many fish here or many birds, what kind of pattern do they form? Do they take up, okay? So, or we want to ask the question, so what kind of interaction they have with their neighbors, okay? We want to ask this. And this question has been asked by many, many people over many, many years. Here is just one example, okay? Daniel Weihs. He was on the West Coast, I think Caltech. And then he moved, one second. And then he moved to Israel, to Technion, okay? So 50 years ago, he asked this question about fish swimming. And he conjectured that a fish school should take up a diamond crystal shape, like this one, okay? You see all the individual fish, they go like that. And each of them also generating this interesting inverted von Karman. You see here, the two work together, have a jet like that, then like that, like that, like that, okay? And here is a jet, if you want. Overall, that's a jet. If you are a follower fish, you don't want to stay right here, okay? Because you don't want to face a jet from your upstream neighbor. But here you see down below here, for this row, the eddy is spinning this way, and this way. And here is spinning this way, and this way, and this way. So geometrically, it looks like you have a return flow here between the eddies. So for follower fish, maybe it's better if you place yourself like this, between the two wake of the fish, okay? So that this guy should also stay in the middle, but behind the two fish like this, okay? So having many fish, taking this point into account, you have a diamond crystal forming, okay? But the trouble is, in nature, we never saw such a pattern with fish. What's going on? So the question has been lingering around for many years, okay? And we try to study this with a very simple approach. For example, here, that's one set of the experiment, the photo taken from New York, okay? So again, here, we have two wings here. And here we have a shaft is driven to flap up and down with speed v, okay? Up and down like that. And each wing is free to rotate. This guy and this guy is free to rotate. So their separation, you can also choose the separation by themselves. You don't do anything, okay? Their flapping speed, the separation, and what is, how do you call it? Direction. You don't do anything. The only thing you put in is a vertical flap, and then you look at the solution. Okay, so the wing shape, again, is this NACA 17. So we printed, 3D printed with 3D printer. PLA, that's kind of plastic, okay? The size of this guy is only a few centimeters, this guy, okay? Into the screen, this wing is 15 centimeters, quite large. So we flap this guy up and down and see what happens, okay? So what we find is, clearly there's a leader, okay? The two will form a little group. There's a leader. Let's put it black here, putting on line 0 here, okay? And then the second wing would stay in a fixed position like this, or another one, or another one. If you put this by hand, if you put somewhere here, this blue wing will fall into this position. If you put a little later, okay, sorry, if you put behind, it will catch up to this position again. As if here you have a well. It's like you have a potential, this guy will fall into this well. Of course, everything's moving forward at the same speed, okay? So here you have another well, and then you have another well, okay? So we worked this experiment with a different frequency, and you have the same solution. For different frequency, you fall into the same position. What is this position? Okay, that's G, that's a gap over lambda. What is the lambda? Lambda is the wavelength traced traced in space by this leader. It's carved a little trajectory in the space. So the periodicity, that's a lambda, okay? That's a constant for this wing, okay? Yeah, because the wing doesn't really see, the leader doesn't see anything behind, okay? So this guy, the second wing will fall into the behind the leader by either 1 lambda or 2 lambda or 3. Further, it's not stable enough. We don't see anything, okay? All right. So in the experiment, we try to push the second wing. While this guy, the 2 wings are flying forward, we can give a little torque here. Try to push the follower to be a little closer to the leader. We give a force here, okay? The torque divided by the length, that's a force, okay? And then see what happens. Or we can apply another torque, try to slow the follower down a little bit, try to move it forward and see if this follower can still catch up. So what we are doing is to give a perturbation to the second wing, to the follower, to probe what is the potential felt by the second wing, by the follower, okay? Okay, so here's the result. G here, again, is a gap between the 2 wings. Lambda is the wavelength again, okay? So what we see is if we push the wing towards the leader, here's the leader, okay? 0 on this axis, okay? This is leader. If we push this guy to the leader, you need a higher and a higher force to do that, okay? If you want to push it to here, you need this much of force. But if you want to put it away, you need higher and higher force, but in another direction, okay. If you integrate this force over this distance, over this equilibrium distance from this point, okay, sorry. Then what you get? Force integrated over space, you get a potential. So you get a potential like that. And then the second potential looks like that. The third one looks like that. Okay. So for the first time, we probe the potential, energy, the curve felt by the follower. If you are here, you will fall into the potential here to the bottom. If you're here, you also fall into that. But if you're here, you have to make a decision. Either go to the first well or go to the second well, okay? And so on and so forth, yeah. All right. So it looks like I'm a little slow today, but we're still doing okay, yeah. So the previous experiment for the 2 wings, we have the 2 hydrofoils or the 2 wings, they have the same frequency and the same amplitude because I impose the same frequency and the same amplitude, okay? So what we observe is we observe so-called coherent motion. That means they move together. And also we have different stable locking positions corresponding to the 3 different wells I just showed you, okay? Then we ask the question, what about the 2 independent wings? Meaning that each wing will take a different frequency and different amplitude. That's very challenging, I have to say, to do the experiment. Maybe slightly easier to do the simulations, okay? Then we wanna, find out what will happen, but let me first tell you how we do that, okay? So how we did that is we flap the leader by 1 shaft, okay? But this shaft is hollow, it's empty inside. And then through this guy, you have a second shaft driving the follower. They don't have to interfere, okay? But in the experiment, it's very difficult to realize this, okay? But here you have an amplitude A1 for the leader's amplitude, F1 for its frequency, And then for the follower, you could have a totally different amplitude and frequency. And we want to know if these two wings can still fly together, okay? Of course, we have a imposed condition, that is, they all fly on the same level, okay? Their average position overlap, exactly, okay? Yeah. Okay, so here's the setup. So here I have a motor, for example, this guy driving this shaft this way, and then we have another motor driving another way, like that, okay? So here some technical details, if you want. We can look into that, or you can look into the paper that was published last year. And I want to show you a movie, okay? Here's a movie. That's the experimental demonstration. Okay. So here's a big tank. The tank is almost human size. Okay, let me pull out a little bit. You see the computer on the, you see the computer here? So you see the size is almost human size. You see the two wings, the two motors are driving at a different frequency and amplitude and driving two wings. And the two wings are submerged in water. So they can interact through the water, okay? Yeah, all right. What is that? Okay. So what we see here is the following. Let me see. Here, the horizontal axis is time, this time, okay? And then the vertical axis, that's the gap in between, okay? 0 here is the position of the leader. Here's the leader, that's the leader here, okay? Yeah, this is time. So if we go back to the old experiment, if the two frequency and two amplitude is the same, for the two, we know what we should expect. We saw 3 positions. So the follower can either stay at, 1 lambda, that's 1, or 2 lambda, or 3. You see the first well, potential well is very tight. You don't have much wandering for the follower. But for the second, it's a little loose. The third is a little wandering because your potential well is a little shallow there, okay? You see how many flaps we have? We have more than 100 flaps. So this is a quite long time series, okay? And then you could also have a different state. You could have stable cycles when you have a condition like the frequency of the follower is smaller than the leader, but the overall flapping speed, that's the flapping speed of the follower, is greater than the leader. What you have is the follower will come narrow down with the leader and then stay far away and then come back again, and oscillation. You have cycles, okay? And then you have also third behavior. That is, once you have another condition, once the frequency of the follower is greater than the leader, but the flapping speed is lower than the leader's speed, okay? By the way, for the moment, I don't want you to remember all that because I want to repeat in a phase diagram again and again later, okay? So here, the third behavior is there's a threshold distance. If you're further away from this threshold distance, you will fall off. You will never catch up with the leader. But if you are closer than the threshold distance, you will come very close to the leader, okay? So here you have 4 different examples. Clearly here, you can see 3 types of different behaviors. Unstable at the bottom, and the stable cycles, or multiple stable locking positions, okay? Different behaviors, okay. So here again, let me show you some result. The horizontal axis is a gap, okay? Gap over lambda 1. Lambda 1 is the leader's wavelengths, okay? They're similar anyway, okay? That's a gap. So the leader sits here, okay? The vertical axis is the amplitude ratio between the two. So here you have above this dashed line, you have the follower flapping with greater amplitude. Here, the follower flap at a smaller amplitude. Okay. So if they are exactly the same, for example, here, for this diagram, we have the same frequency, okay? The frequency of the two is the same. So once A2 over A1 is 1, that means the same frequency, same amplitude. Again, what we have three potential wells. That's a stable, three potential stable positions. So I'm repeating my result, but if I increase amplitude, what you see is, if I increase the amplitude of the follower, it will move little closer. The follower will move little closer to the leader, but still stable, okay? Still stable. You still have a dot here, well-defined. But if you move at a smaller amplitude than the leader, you stay a little behind, but still locking in a position. The same for the second well, same for the third. But we find this guy. This guy shows if the follower is very close to the leader, you only need to flap 1/3 of the amplitude, but you can still catch up, okay? We call it free loading. It's like you ride a bicycle behind the bus, behind the car. I don't recommend you should do that, but you see the idea, okay? So here is a very small amplitude follower, 1/3 of the leader. You can still form a nice school and move forward, okay? If you change the relative phase, you give them 1/4 pi, 1/2 pi, or 3/4 of pi, you can fill out a space here. You can find, for example, this guy, that's a half 180 degrees apart from the leader. You can find this stable position, and this stable position, and this stable position, and this stable position, okay? Yeah. And then if you continually change the phase, you can cover the entire stable region, this part, this yellow part, okay? All right, so by changing the phase, you can change your position. You can change your position of your well, okay? Yeah. All right. Now I want to relax my conditions. I want to change my frequency as well. So the horizontal axis becomes the ratio of frequency. 1 is here. The amplitude ratio is here. 1 is here. So we have been discussing a lot for this, okay? That's the same frequency, same amplitude, okay? And then A1 and F1 equals A2 F2 is this dashed line like this. This area indicates, okay, this area indicates the follower has a higher flapping speed than the leader. And this means the follower has a smaller flapping speed than the leader, okay? If the two wings did not interact at all through the fluid, they only fly by themselves, you can easily imagine for the follower with a greater flapping speed, you will collide with the leader, right? Because you are flying faster, but you are sitting behind, then you have to collide. And if the follower is flapping at a smaller speed, because this guy is the speed, okay? Smaller speed, but you are sitting behind, you are trailing off. You separate from the leader, okay? Okay, so that's the imaginary phase diagram, if you want, for two wings did not interact hydrodynamically. But in reality, it is like that. You have a stable cycle like that, okay? You have stable positions like that, we've been talking, And you have unstable positions like that. The three different states we have discussed in the previous two slides, okay? All right. Oh, I'm taking too much time today because I was telling too much stories, okay? Okay, I'm going to skip this movie because that shows basically the result, more visually. So the key to understand the phenomena is the following. The thrust force, F of t, scales with flapping speed squared. That's a thrust force coefficient, CT. CS, that's the area of a wing. Rho is the density of the fluid, okay? And the V here is AF. Here I have a factor of pi, okay? To honor Zhu Chongzhi today. Well, that's a joke. This pi is always there, okay? All right, so this is the expression for any wing that flaps in a quiescent fluid, okay? The fluid is quiet before the wing encounters the fluid. That's quiescent fluid. But in reality, the wing will encounter the flow pattern left by the leader. So you really have to make a difference of this V, here the V, minus the flow speed, the difference, squared it, okay? The rest is the same, okay? Yeah. So here, for example, that's a leader. The leader left alternating flow pattern like this, okay? Up and down, up and down. So you can imagine the inverted Van Karman straight looking like that. But I'm only taking the vertical component here, okay? But also the wake structure will diffuse, will get weaker over time. You see the arrow comes from bigger to small. So I will put a factor e to the minus delta t divided by tau here. That's a weakening factor, okay? Decaying factor here. I put that in. This can be experimentally estimated. And then, okay, for the second wing, for the thrust, so what I can do is, here is the prefactors. That's A2, F2, that's the flapping speed. That's your own flapping frequency, minus the flow structure. That's the flow structure we just discussed here, okay? With a decaying factor, but it's modulated by the first wing, okay? It shares the first wing's trajectory. It has a similar expression. So we take a difference between the actuation of the follower, take a difference with the flow structure left by the leader, you squared it, you take average, that's integrate, that's an integral, okay? And then you can simulate the two particles, basically. Of course, the leader does not it is not affected by the follower, but the follower is strongly affected by the leader, by the wake, okay? So the background color shows when collision happens from the model, and here the green part, that's a stable cycles. They also recover from the model that coincide largely with the experimental data. Of course, this is a part that does not coincide, okay? And here's the unstable positions. We also have overlap between the models, between the model and the experimental observation here, okay? Yeah. I understand this phase diagram is not very kind of straightforward. It's not too easy to digest. Once in a while, if I don't have to look at this one recently, I really have to spend a few more minutes to understand it. I hope I've told you the story, okay? Okay, so come back to the old question. Can we ever see a fish school or bird flock that resembles a crystal, like what was shown in Weihs' model in 72, 73, like this, okay? Here, in our experiment, looks like we have 3 well-defined locking positions, but these 2 wings, they take the 2 same amplitude, frequency, and phase. If you change the relative phase, this well, the position of this well and this guy can shift to any point in space, which means if this fish takes a different phase, okay, than the leaders, this guy can find a stable position anywhere in the neighborhood to find the force benefit, okay? And there's no reason for all these fish to swim exactly in phase. That's why leading to the conclusion, I mean, for us, we will never see a fish crystal in nature because they don't take the same phase, okay? So now, today, we are relaxing the constraints. We look at 2 flapping wings, but we separate the 2 swimmers by a lateral distance, L, and then we watch how they behave, okay? So I can tell you a little bit, I can release a little bit of the secret. The paper was submitted. Only today we heard the journal send the paper for review, which is nice. So the main result is when the 2 wings, they swim side by side, they will influence each other with much longer distance than the case if they stay exactly behind each other, okay? That was a surprise. Another surprise is if they swim side by side with the same X position, they will increase their swimming speed by up to 60%, okay? That's a lot. Can you imagine if someone suddenly swim 60% faster? That is quite an improvement. So we're still looking into fish pattern or bird pattern. For example, here's a photo I found from the internet. A lot of birds, flamingos, taking off from the ground, from a lake. It looks like we are beginning to see a crystal, but we are really looking into the issue very seriously and try to see if nature really can form a crystal of individual animals, okay? So here I have a movie of a swan taking off from a lake. You see how difficult this guy works. Because it's difficult, with a little help from the neighbor, or the neighbor didn't help at all, will make a huge difference, I suppose, okay? So that we hope that we will find how fish work together, what kind of pattern they form. But to close, I want to thank my collaborators, Steve Childress, Nicholas Vandenberg, with whom I work with on the bifurcation for the symmetric way, okay? And then Max Shelley and Silas Albon, they work on the numerics for the bifurcation in the numeric simulations, okay? And then I have Sophie and Joe and Life. We work on the group locomotion for the individual flyers, right? So we are still learning to swim, to fly in the laboratory. With very simple systems, we reduce a bird or fish only to a hydrofoil or aerofoil, which is a wing, okay? So I forgot my take-home messages. So what I learned personally is the simple physics or mathematical models will give rise to a solid base for biological locomotion, okay? We try to remove the social behavior from what we observe in nature, because the idea is the in the biological world, okay, physical laws may not dictate, but nobody should work against physical interactions. Okay, that said, I want to say physical interactions will give us a nice foundation about which we can talk about social behaviors. With that, I really want to thank you for your time. And this is, I'm over time by 8
fine.
minutes.
Yeah.
Yeah, thank you.
Okay.
Yeah.
Thank you, Professor Zhang. Yeah, any question for Professor Zhang?
Hi, Professor John.
Hey.
Thank you, Professor Liu. I have a question.
Yes.
Please.
In your experiment, the wings you made are made of plastic. I'm wondering if you have tried other material, and would that affect your result? Thank you so much.
Sure. That's an interesting question. Actually, I guess you're talking about density, right? Not flexibility. Right.
Yeah,
So,
density and the interaction with the fluid.
Right. Density-wise, you see all our wings are kind of prescribed. They have a prescribed flapping vertical speed. But the forward speed is a result of interaction with the fluid with each other. So if something is too heavy, say if I take a plastic that has a density like a 1.2 times of water, but then another wing is 20 times of water. Like say the wing was made with gold if we had the money, okay? And then I would say the behavior would be different because inertia here is important in the model, okay? Because we're talking about forces. So
Yes.
for example, this stable cycles, for that state, you can imagine if I have a very heavy wing, this cycle will be much longer. If I have a very light wing, the cycle will be much faster. We probably don't even have the same states. So I don't know. So far we only used wings with a density slightly greater than the fluid, like 50% or so. Yeah.
Okay, and what material do you use? Like what kind of plastic?
We use this so-called PLA or ABS. It's a very common material for 3D printers.
Okay, okay.
Yeah, but don't
So
forget, my serving system also has added mass to that. So if I talk about the mass or density, I should take that into account as well, okay? But I believe numerical simulation can answer this question better.
thank you so much.
Sure, thank you.
Any more questions for Professor Zhang?
Oh, hi.
Yes.
This is
Hi.
Zhiliang Xu. Oh, sorry.
Go ahead. Go ahead.
Please.
Okay. Thank you. So this is Zhiliang Xu from Notre Dame. I have a probably unrelevant question. So
Yep.
Professor Zhang, you talk about this group behavior at the macro scale, but at the micro scale, there is bacteria swarming.
Yes.
In which bacteria also do this kind of collective motion. So could you please give us some insight on similarities and the differences between those two social behaviors at very different scales?
Okay, that's a great question. It's a little hard to answer. Here, I want to take this slide. I don't know if you still see my slide.
Yeah.
Oh, you see it, okay. You see the Reynolds number for large bird or large fish. We are talking about very high Reynolds number. It means the inertial force is dominating, okay? So that the force scales with any speed or velocity with a quadratic relationship, okay, squared. But in the bacterial regime, the Rayleigh number is, say, 10 to the minus 4 for E. coli, for example. It's very small, maybe even smaller than that, 10 to the minus 6. I don't have a number for that on top of my head. So there's no wake, there's no flow structure left by E. coli. However, they do interact with each other. For example, when they are close with each other, their flagella will influence the fluid, okay?
Yes.
And the fluid might be viscoelastic. That could give rise to some fanning effects. And also, this E. coli might leave some chemical trace that affect the fluid hydrodynamically. That's also possible. But what I want to emphasize now here is that E. coli don't leave hydrodynamic wake like the ones we are discussing now here. Right? It's a very different regime, but it's also very interesting because, for example, people talking about low Reynolds number turbulence. For example, you have a swarm of bacteria. They form a pattern that's sharing some characteristic of turbulence, okay? That is something you never expect at a very low Reynolds number, okay? That's a very different, question in a very different regime that I'm not good at, okay?
Yeah, the question is bacteria is a dilute suspension or concentrate? What's what do you study in these things like very concentrate, very dilute, but bacteria is how please?
They vary. So they vary from like a dilute to a very dense concentration. Yeah.
Right.
So then in this case, behavior will be very different, right? In terms of hydrodynamic contribution.
Right. I guess because I heard the word swarming, so that means that the concentration is quite high. It's almost touching, right? Yeah. And in that region, you really have a very extremely high called factor, packing factor. I forgot what's the word for that. Yeah. Packing fraction.
Any more questions for Professor Zhang?
Yes. So here's Kai Huang from DKU.
Hey.
I would like to ask a question, a technical question about experiments.
Yep.
Where you're doing the experiments, you're driving it vertically. Are you able to get the power that you spend on the lead and the follower? And how would that power, fluctuate? Right? Yes. Okay. You know the force, you know the velocity, right?
I guess in principle we could get that. That's a very good question also, okay? For example, here we could place a force sensor, right? Somewhere here. Here we also place a force sensor on the shaft, okay? So we know how much force we need to drive each of the wing. And then we know how long they travel. So we could maybe easily calculate the power consumption to drive each of them. But we haven't done that. I believe there's a technical difficulty here. We haven't done that. Okay.
Okay. The reason behind that is actually I want to ask. I keep wondering if there's a flock of fish or bird. Is there any specific properties that a leader should have in comparison to follower? So let's say the drag coefficient. So depending on the shape, we are tuning the shape, right? Yep. This is tuning the drag coefficient. And would it be, I'm just wondering naively, how would the leader has a different drag coefficient? Is it may have a different drag coefficient in comparison to the follower, or should it be stronger in comparison to the follower? So this is something I had in mind, and maybe you can answer the question.
Interesting question. I have some answers for you. Okay, let me comment a little bit on your previous question before I answer this question. Okay, so far we have been working on the kinetics. What kind of stable positions they form? What kind of forces they form? we have not talked about energy. I believe the next 10 years, we will be working on many other groups. So we will be working on the energetics, how much energy we spend to do all that, okay? Okay, so that finishes your previous question. Your second question, I don't have a direct answer, but I can tell you one experiment we did 12 years ago, okay? If I put two flexible flags, okay? Flapping flags, okay? And then we put in the wind. We measure the force acting on each flag, okay? So we know for two cylinders, if we put a leading cylinder, a second cylinder in a flow, the leader has more drag than the follower. It's like the leader cyclist, if you take a bicycle, if you lead, you have more drag than the follower, okay? But for two flapping flags, the leader has a lower drag than the follower, okay? Yeah, it's the opposite. So if you want, please let me do a little shameless advertisement. Please go to my website. There's a paper in 2008. We talk about inverted drafting. So when you have two flexible structures in the flow, the drag relationship is opposite. We vaguely explain it, but not to the hard details. Okay? But we did observe this in the experiment. Very solid data. Okay.
Okay.
Yeah.
So that means that depending on the drag coefficient of the leader, then the potential veil, you see that the potential veil actually has a decay, right, from the result you showed. This decay might be different, looks like absolutely different. But this is a tuning factor, right? Okay.
I agree, yes. You see how the weight decays. And also, it could be a function of Reynolds number, right? For small Reynolds number, it decays immediately, right? For high Reynolds number, the weight can persist for some longer time, right? Yeah, okay. So you're right. It's tuned by the Reynolds number.
Thank you.
Yeah, thanks.
All right, so any more questions? If not, let's thank Professor Zhang again for the wonderful talk.
Thank you. Thanks so much.
Yeah.
Okay.
Thank you. Thank you.
Yeah.
Thank.
I will stay a little bit.
Yeah, in case.
Okay.世新怎么样？那个还清楚吧？
非常清楚，麻烦你，谢谢您，谢谢您，张老师。
这清楚，我的声音还是清楚投射出去了哈。
是的，是的，是的。
因为有时候这个，我可能是觉得我这个时间比较多呢，我就刚开始放慢了不少。
没关系的，没关系的，非常之好。
OK。
对。
So